Welcome to the third installment of Dr. Eigenstate Explains, a series for those who might be watching this one before any of the other ones, where I take some interesting or advanced or complicated concepts in various areas of science, mainly astrophysics, cosmology, quantum mechanics, and try to explain them in a way that retains some of the technicalities and nuances that I feel are important to understanding that concept, but still delivers the concept in a manner palatable for somebody who might not have a very technical understanding of the subject. This one, first off, I know it's been normally I release these Thursdays, 7 p.m. Central Standard Time. I had some stuff going on. I'm not going to get into details, nothing bad or anything, but had some stuff going on. Couldn't get it recorded until today. I'm going to release it today. Normally I record them on Wednesday, release them on Thursday. I will also be releasing another one this Thursday at 7 p.m. Central Standard Time, so be sure to tune into that. This one will probably be a little bit shorter. I'm betting it'll be a little bit shorter than the previous two. This concept isn't really that difficult. There's not as much meat in it that we need to cut through, that we need to cook up, so to speak, not as much to cover. But in this one, we will be talking about an interesting concept, and anybody that has heard anything about quantum mechanics has probably at least heard this term. In today's video, we are going to be talking about wave-particle duality. And this really is a rather interesting and seemingly non-intuitive concept that came about actually kind of slowly in quantum mechanics. It started with a guy by the name of Max Planck. Not Planck, Planck. Got to get your pronunciations right. And he was doing research in things like thermodynamics and black body radiation, things of that sort. A lot of stuff in work in thermodynamics. And one thing that he noted about energy, especially black body radiation, is that when it is received by some other material or detector or what have you, when the energy emitted via black body radiation is imparted onto some other object, it does not come in a continuous stream as you would imagine it might. What happens is it comes in discrete chunks with these gaps in between it. So it comes in these little chunks of energy instead of being imparted continuously, which is really, really interesting. So what he said is that the energy is quantized. It comes in little quanta would be the plural, quanta of energy. And that's where we get quantum from in quantum mechanics. This really was the first thing that sort of led us down the path to discovering wave-particle duality, so to speak. Is that the energy is imparted to an object in discrete chunks or discrete quanta of energy, not continuously. And then Albert Einstein comes along, and he performed something that was called the photoelectric effect. He actually won the Nobel Prize in physics for this. He did not for relativity, unfortunately. I still think he should have. I've actually found that quite a few people agree with me. And yes, I am going to color this in, so this might take just a couple of seconds. But I'm a perfectionist, so I can't forget that little bit there. What Albert Einstein noted in his photoelectric effect, should I get this, it's the same size roughly. What Albert Einstein noted in his photoelectric effect is if we have a piece of metal, and this is going to be our piece of metal, what he noted is that if you shine some light on it, shine some light on it. Ooh, Guts of Gibbons live. If you shine some light on it, what happens is you'll get little electrons flying off of it. They're all generally going the same direction, so don't worry about the direction which the arrow's pointing. This was rather interesting. And the most interesting part about it was that these electrons over here, the energy that they carried with them was directly proportional to the frequency of the light hitting the metal, which is an interesting proportionality. This actually helped to corroborate what Max Planck said, because what this means is that the light, knowing that we knew at this time that it acted like a wave, but that the energy that it carried must be deposited or imparted onto the metal in discrete chunks of energy, and that if those chunks had enough energy, they could actually knock electrons loose. This gave rise to something that we now call a photon. Actually, I think the concept might have been hypothesized a little bit prior to Einstein, but this really solidified the idea that light is carried in discrete chunks of energy, and we can call those photons. This was another big step in developing wave-particle duality. The idea, which is the idea that an object, a quantum mechanical object, can exhibit both wave-like properties and particle-like properties, and it really comes down to how you're interacting or measuring that quantum object. The big thing that really nailed down wave-particle duality for us is something that I'm not going to go deep into, because anybody that's watched any quantum mechanics or does watch quantum mechanics videos on YouTube has probably heard about it 1.5 million times and seen just as many videos on it, and that's the double slit experiment. I'm not doing a video on one. Please don't ask me. Too many people have already done one. I'm not getting involved with that rodeo. But what the double slit experiment tells us is that if we take a beam of electrons and we fire them at this I don't really want to say, we'll just call it an apparatus that has 2 slits in it, a thin sheet of some material with 2 slits in it. Well, what we would expect is that on the detector screen on the other side of that slit, of those 2 slits in that apparatus is what we're going to call it, you would expect to see something like and I know they're not all the same size, some will look like lines, some look like dots, but you would expect to see on the other side of the apparatus with the slits in it, where the detector screen is, 2 places where the electrons hit at. That's not what we saw. What we did see was something akin, much more akin, it wasn't really akin to, it was an interference pattern, which looked something more like, and I'm going to try to do this, make sure I can do this right, and then we're going to get a little bit darker and a little bit more filled in. Then we're going to get really, really dark and really, really filled in. The darkness and the filled-inness, I guess you could say, of the area indicates more electrons being there. And then we go back, not quite as dark, and then it's really faint. You get an interference pattern. Well, interference patterns are things that waves do when they're put through a medium, and then they separate into 2 waves that can constructively interfere and destructively interfere. And so these places like here or here or here are places where it constructively interferes, and then the empty spaces here in here, I should do that in another color. The empty spaces in between are places where it would destructively interfere. And that was a little weird because we thought that electrons were, particles. Why are they acting like waves? This is really weird. We need to figure out why they're doing this. So we put detectors, ultimately we put them on one side of the apparatus and on the other. We put them on both sides of the apparatus before they went through it, after they went through it, but before they were detected by the detector screen. And every time we did that, we would get the initial pattern, or the pattern we initially thought we would get, of there being electrons in 2 positions, bunched up in 2 positions on the detector screen, indicating that they had went through one of the slits or the other. And then when we shut those detectors off, we got the interference pattern again. We turned them back on. We got this again, back and forth, back and forth. Nobody knows what's going on. Well, what this really solidified is the notion that quantum objects can behave like waves, and they can behave like particles, which is really the crux of what wave-particle duality is. Now, there's a question that's often asked, and it is often asked in entry-level quantum mechanics courses, but it will be answered generally a little bit differently in those courses versus advanced quantum mechanics. And that question is, take some quantum object like an electron. Is it a wave or is it a particle? Some people might answer both. Some people might answer neither. Some people might answer, well, yes. Just answer yes to it. Is it a wave or a particle? Yes. The actual answer, and we know this from quantum field theory, is it's a wave. There are always waves. The reason that we say wave-particle duality is because, let's draw a little coordinate space here, is because of what happens when we interact with a quantum object. It's still a wave, but what we would say is that its waviness has been reduced to being, we've reduced its waviness. Its waviness has been very localized so that the behavior of the wave will be more particle-like. So you've got some, let's say, interference pattern. I know it looks poor, bear with me. I'm not an artist, I'm not trying to be an artist. You've got some interference pattern, and then you want to say, you know, if you got your probability, highest probability being here, lowest probability being here, you've got probabilities in between. The higher the amplitude, the higher the probability, yada yada rama rama ding dong, everybody should know that. And then when you make a measurement or something like that, you get it, and it collapses to one of those locations. So what this means is that if you notice, this is still actually technically a wave, or a wave function. It's just that the waviness has been reduced. It's very localized. And what we can do is we can say that there are standard deviations here. And you'll notice that this localized wave, the one here in yellow, is inside of a standard deviation. Namely, I didn't trace that very well, that one right there. You're just localizing the wave. You're reducing, you're lowering the standard deviation, the deviation of it. So that wave is only present within one standard deviation, but not in the others. What this means is that it's still a wave, it's just that it's because it's within a standard deviation, one can confidently say that that is very, very likely the measurement that you got. That we can confidently say that this is the measurement that we can then associate with that quantum object. So wave-particle duality is a thing, but they're always waves. What it's telling us is that there are instances where the waves are so localized that they exhibit particle-like behavior due to the reduction in the standard deviations over which that wave or the wave function is spread. And that sort of sums up what wave-particle duality is. Wave-particle duality is the concept in quantum mechanics that quantum objects can exhibit behavior that's very wave-like and behavior that's very particle-like. And in most instances, it depends on how you're measuring that quantum object or interacting with it. But if you ask the question, well, is it a wave or is it a particle? The technically correct answer is it's a wave. It's always a wave. It's just that you can localize, by interacting with that wave, you can localize it, which gives you a quantity that can be reasonably considered because it's within one standard deviation. So that is what wave-particle duality is. And that sort of answers the question of is it a wave or is it a particle? It's a wave. And again, quantum field theory tells us that what particles are just localized waves or wave packets in a quantum field. And when we think about wave-particle duality, we can think of it can lead us to think about some other interesting concepts in quantum mechanics. One of those is, and I believe it was Niels Bohr. Somebody correct me in the comments or in the live chat, since this will be premiered live, if I got that wrong, but I believe it's Niels Bohr talked about related wave-particle duality to a concept called and I understand my handwriting is bad, it's always been bad, complementarity. Complementarity is the idea in quantum mechanics, the concept that you can have two quantities, two observables that are complementary to one another, which means that when you interact with a system, the way you interact with it that gives you knowledge about what one of these quantities is, that tells you what that quantity is as it is associated with that quantum object, means that you would know less about the other quantity that is associated with that is complementary to that. And that is probably already bringing up some interesting things that many of you have probably heard of. But I'm not going to touch on that right now. That will be in a video released later this week, where we will touch on that concept. But in this video, I just wanted to provide a brief overview of what wave-particle duality is, the concept in quantum mechanics that quantum objects can exhibit wave-like behavior and they can exhibit particle-like behavior, generally reducing to how you're interacting with that quantum object, but that fundamentally, through quantum field theory, quantum objects are always waves. We can just localize those waves to within a standard deviation. We can lower their standard deviation, which gives us a high degree of confidence for what quantities we are measuring for that observable or for the whatever thing it is we're trying to measure. So hopefully that gives everybody a good idea of what wave-particle duality is, and until the next video, per causam nos perfectum, or through reason we progress.